So if phi and psi are integrable, phi minus psi are integrable. Therefore, the negative part of phi minus psi, that is this function, is integrable. So phi subtract this function is also integrable. That is the minimum of phi and psi is integrable. Okay. So you only need to prove this equality, but this is very easy. For example, I will prove this here. If phi x less than psi x, then phi minus psi negative part of this function is 0, and the right hand side is psi x minus x is psi x, and the no, sorry, not 0. I make a mistake. If phi is less than psi, then phi minus psi, this is the minus how to say is psi x minus phi x. Okay, by the definition of negative part of a function, when phi x is less than psi x, the negative part of phi minus psi is psi x minus phi x. Therefore, the right hand side is psi x subtract the difference of psi x and phi x. This is phi x. But the left hand side, minimum of phi x and psi x is also phi x. Okay, and in a similar manner, you can prove that if phi x is not less than psi x, the equality is also true. Therefore, this equality is true. So we have proved this equality. So from this equality, we see that if phi and psi are integrable, then the minimum of these two functions is also integrable over the rectangle, and you can also establish the similar property for maximum. So if phi and psi are integrable, then the maximum of phi and psi is also integrable. Okay, so with this preparation, we can assume what we are going to do. We want to prove that if f is integrable over d1 and d2, then it is integrable over the union of d1 and d2, that is our d. Also integrable over the intersection of d1 and d2. Also, this equality is also true. This is what we need to prove. Okay, we are not doing this. Now, before proving this, we have used this page to discuss the relation of the integrability of a function and its absolute value function. Using absolute value, we can define the positive part and negative part. And using that positive part and the negative part, we can discuss the integrability of the minimum and the maximum of two integrable functions. Okay, so with this preparation, we assume that f is integrable over d1, and it is also integrable over d2. Then, by definition, the zero extension of f outside d1 is integrable over the rectangle I containing d, and the zero extension of f outside d2 is also integrable over I. Now we remind you that the definition of f d1 and f d2. F d1x is fx for x in d1, 0 for x not in d1, and f d2 is similar. Fx for x in d2, 0 for x not in d2. Okay, so these are the definition of FD1 and the FD2. Now, using the definition of FD1 and FD2, we have important observation. FD1 over intersect with D2. This is the minimum of FD1 and FD2. This can easily be proved. So this is D1 and this is D2. Okay. So the intersection is here. So if a point is in the intersection, if a point is in the intersection here, then FD1 and FD2 are equal to fx. Therefore, the value is fx. Both sides, the left hand side and the right hand side, both the left hand side and the right hand side equal fx. That is, x in the intersection. Both sides, left hand side is fx. It is also the right hand side. So if x is not in the intersection, suppose f not in D1. F not in D1 means f D1x is 0. Therefore, the right hand side is 0. Okay. To make our argument work, we need to assume that f is non-negative. We study the non-negative function first. Okay. So we assume that f is non-negative. So if f is non-negative, when x not belongs to as before, if x is a point in the intersection of D1 and D2, then both sides of the equality we want to prove equals fx, and the equality is true. But if x is not a point in the intersection, we might assume that x is not in D1. Then x is not a point in the intersection means that the value of the left hand side at x is 0. But since x is not in D1, the value of fD1 at x is 0. And f is non-negative, therefore the right hand side is also 0. Because fD2 might be 0 or might be positive. Because our function f is non-negative. fD2x could not be negative. So the minimum of 0 and the non-negative function is 0. So in this case, both sides are also 0. So this means that the equality is also true if x is not a point in the intersection. So this prove this equality. Okay, the equality in the red box. So by our previous argument, we know that fD1 intersect with D2 as the minimum of fD1 and fD2 belongs to is integrable over the rectangle I. Okay, maybe I will erase this to make space for so that I can complete the proof of this theorem in this page. Okay, so as we said, because fD1 and fD2 are integrable over I, therefore the minimum of fD1 and fD2 also integrable over I. Okay, consequently, we also know that this means that fD1, D2 is integrable over I. Sorry, this means that f is integrable over the intersection. So this part of the theorem, we want to prove that if f is integrable over D1 and D2, then it is integrable over the union and over the intersection. Now we have already proved that it is integrable over the intersection. To prove that it is integrable over the union, we see that f d1, the union, can be expressed by f d1 plus f d2 minus f d1 intersect with d2. So this equality can be proved very easily by taking different different x from d1 and d2 and the intersection. In every case, the equality is true. So this is true for every x in I, in the rectangle. So the three terms in the right hand side are all integrable over the rectangle. Therefore, their linear combination, that is the right hand side, that is our f d1, the union of d1 and d2, is integrable over the rectangle I. Okay, so this means that f is integrable over the union. And moreover, the value of the integral d1, d2, actually this is f. This is, d1, d2 is d, union is d. So this equals, by definition, f d1, d2. But using the equality, using this equality, and using the linear combination property of integral over rectangle we have proved in the last lecture, we know that this can be expressed by I f d1 plus I f d2 minus I f d1 intersect with d2. But this integral are precisely the integrals of f d1. The integral of f d1 over I is precisely the integral of f over d1. Similarly, the other two integrals are precisely d2 minus d1 intersect with d2. So this proved our theorem for the case that f is non-negative, because to establish the equality, we need f to be non-negative. Okay. So when f is non-negative, if f is integrable over d1 and d2, we have proved that f is integrable over the union of d1 and d2, and also over the intersection of d1 and d2, and also the integral equality is also true. But this does not complete the proof, because our proof up to now depends on an additional assumption that f is non-negative. Okay, so we still need to prove the case when f is sign changing. So for general f, that is f is neither non-negative or no positive. But we can always write f to be the positive part minus the negative part. Here, f positive negative is absolute value of f. We discussed this previously. Okay, so we see that f is integral over d. Then f positive and negative, maybe I should write d1 and d2. d1 and f is integrable over d2. Then we have the positive part and the negative part integrable over d1 and d2. Therefore, the integral part is integrable using the result, because both f positive part is no negative, negative part is also no negative. So we can apply the previous result to f plus and f minus to see that f plus is integrable in over d1 intersect with d2, and also for the negative part the result is also true. And also we also have d1 d2 f. Applying the previous result to f plus and f minus, we will get d1f plus d2f minus d1 intersect with d2. Okay, then since f plus and f minus are all integrable over the union and the intersection by our previous linear combination property, because f is the linear combination of two non-negative integrable functions. So by the linear combination property, we conclude that f is integrable in the union and over the intersection. And also the value of f at d can be, d is d1 union d2, can be written as d1 d2 f plus minus d1 d2 f minus. Then you use the result here. You use this result, the result expressed in the last two lines of this page. Applying this result, because this result is true for non-negative function, applying this result to our f plus and f minus, and eventually you will find that this is d1f plus d2f minus d1 union intersect d2f, and this completes the proof of our theorem. Okay.